Hi everyone. Today we're going to be talking about posets, or in this video we're going to be talking about posets. I guess it's today, whatever day you're watching it. But first we're going to recall the definition of a binary relation, because that is the data involved in a poset. By definition, a binary relation on a set X is a subset R of X cross X. And remember that X cross X, this is the Cartesian product of X with itself. So the elements of X cross X are just pairs X comma Y, where X is an X and Y is also an X. And so a binary relation, it's just a subset. There's no conditions at all on it. If X comma Y is in the binary relation, then we write X R Y, and we say that X is related to Y. So let's give some examples. So here are two examples of binary relations, both on the set X, which consists of the numbers 1, 2, 3, and 4. So here the binary relation consists of the pairs 1, 1, 2, 2, 3, 3, 4, 4, 1, 2, 1, 3, and 2, 3. And so I've drawn it here. I've drawn X cross X. That's what this grid is. And then I've circled all of the elements which are in R. And so, for example, right, because 1 comma 1 is in R, we write 1 R 1. Get one a little bit bigger. And because 2 comma 2 is in there, we write 2 R 2, etc. Great. And then in this example, the same underlying set X, but the binary relation just consists of 1, 1, 2, 2, 3, 3, 4, 4, 1, 2, and 2, 1. And we'll see, so I haven't even told you what the definition of a partial order is, and I haven't even told you what the definition of an equivalence relation is, but we'll see that this one is a partial order, and this one is an equivalence relation. So I'll define these terms, and then we'll see why my claim is true. Great. Okay, so here are the definitions that I was talking about on the previous board. So a partial order on a set X, it's a binary relation, which we just defined on X, and we're going to denote it by less than or equal to typically, which satisfies these three properties. So property number 1 is reflexivity. So this means that for all X in X, X is related to itself. Transitivity is the second property, and this says that if X is related to Y, if X is less than or equal to Y, and Y is less than or equal to Z, then X is less than or equal to Z. Also, people sometimes call this the transitive property, kind of popular. And number 3 is anti-symmetry. So this says that if X is less than or equal to Y, and Y is less than or equal to X, then X and Y must actually be equal. And so, of course, I'll give you tons of examples of partial orders that we see in nature that you've seen before. But the symbol reminds us of the partial order on the real numbers, for example, and the partial order on the real numbers definitely satisfies all three of these things, and you can get your intuition from that. So, for example, in the real numbers, if X is less than or equal to Y and Y is less than or equal to X, then definitely X and Y are equal. Great. So the definition of a partial order may not be super familiar to you, depending on your background, but many more people are familiar with the definition of an equivalence relation. So let's compare and contrast the two. So an equivalence relation on a set is again a binary relation, but this time we're going to denote it by tilde. Tilde on X satisfying reflexivity. So this is the same property here, but here we have different notation for the binary operation. Binary relation. So we've used that notation here. Transitivity, again, same property as before. So if X is equivalent to, in the case of an equivalence relation, instead of saying less than or equal to like we do for partial orders, we say equivalent to. So if X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. But this time it satisfies symmetry instead of anti-symmetry. And symmetry says that if X is equivalent to Y, then Y must be equivalent to X. And we'll see that these two properties, I mean, it's in the name, right? But they're in stark contrast to each other. They create very, very different structures. Great. So in the on the next board, we'll see why the examples that we saw on the previous board were examples of each of these respectively. Okay, so here we're going to compare and contrast equivalence relations and partial orders via the two examples from before. So remember, we had these two examples of binary relations, both on the set 1, 2, 3, 4, and then I circled the elements of the Cartesian product that are in R, that are in the relation. And here were the four properties that we discussed before. So remember reflexivity, transitivity, symmetry, and antisymmetry. And recall that equivalence relations satisfy reflexivity, transitivity, and symmetry, whereas partial orders satisfy reflexivity, transitivity, and antisymmetry. Okay, great. So we have these two examples, and as we said before, this is a partial order. And the top one is a partial order, and the second one is an equivalence relation. Okay, so let's see how we can see these properties in terms of the picture that I've drawn. So first of all, reflexivity says for all x in x, x must be related to x. So that means that every element on the diagonal, right, those are the elements 1, 1, 2, 2, 3, 3, and 4, 4. Those are the elements, those elements must all be circled in our diagram. And so in both of these diagrams, they're both circled, and that's good because this must be true in order for these relations to be either a partial order or an equivalence relation, right? Both partial orders and equivalence relations require reflexivity. Okay, great. Let's do, transitivity says if x is related to y and y is related to z, then x is related to z. And so this is a little bit more difficult to see in the diagram. Maybe it doesn't have a super clear explanation in terms of the diagram, but we can check that this is true on both of these. So for example, here, right, because, so 1 is related to 2, and 2 is related to 3, therefore 1 must be related to 3, and indeed 1 is related to 3. And here, for example, 1 is related to 2, and 2 is related to 1, so 1 must be related to 1, which it is. Great, and you can check that for all other pairs, both of these satisfy transitivity. Symmetry, what does that say? It says if x is related to y and y is related to x, if x is related to y, then y must be related to x. And symmetry, the word is very is almost self-explanatory in terms of the diagram. Symmetry just means that if I reflect the diagram across the diagonal, then I must get back the same diagram. And so that is clearly true of this thing, right? If I reflect it across the diagonal, I get back the same diagram. But that is not at all true of this thing. And that's good because this one is an equivalence relation and this one is a partial order and does not satisfy symmetry. Great, and then antisymmetry says if x is related to y and y is related to x, then x must be equal to y. So what that means is if I reflect the diagram across the diagonal and a circle goes to another circle, that is only possible if the circles lie on the diagonal. And so that is true for this, right? If I reflect this over, the only time a circle gets reflected to a circle is on the diagonal. But that's clearly not true of this example, right? So if I reflect 1, 2, I will get 2, 1, which is also circled, but not on the diagonal. Great. Okay, so I wanted to add an extra remark to our previous examples, which is that if a binary relation is both symmetric and antisymmetric, then so if for any x and y in x, if x is related to y, by symmetry, y must be related to x. But by anti-symmetry, that just means that x must be equal to y, because if x is related to y and y is related to x, then by anti-symmetry, x must be equal to y. So that actually says that r must be contained inside of the diagonal, right? R must be contained inside of the pairs x comma x. And so in particular, if r is a partial order and an equivalence relation, then actually r must be equal to the diagonal, must be equal to the set of pairs x comma x, because of course, if you're a partial order and or an equivalence relation, then you're also satisfy reflexivity, which means that all of these diagonal elements are actually in R to begin with, and so you have equality of these two sets. So this kind of shows you like, this is maybe a good way to contrast equivalence relations and partial orders. They're very different, right? If you have something that's both of them, then it's totally trivial. It's just the diagonal. Fantastic. Okay, so now we're going to talk about posets, finally give the actual definition of poset, the word that's been written there forever. And we're going to give a whole bunch of definitions of various, of like the lingo of posets that we'll use. Okay, so a poset is just a pair, x comma less than, lec is the tech code, x comma less than or equal to, where x is a set and less than or equal to is a partial order on x. So if I have a poset, then if I write x strictly less than y, this means that x is less than or equal to y and x is not equal to y. Just like we do in the normal, the real numbers, like we're used to. X and y are said to be related if either x is less than or equal to y or y is less than or equal to x. Otherwise unrelated. And at this point you're saying, wait a minute, Nate, I'm used to the less than or equal to the partial order less than or equal to on the real numbers where all elements are definitely related. So that's called a total order. We'll talk about that in a second. But for partial orders, this actually does not have to be true. So if you go back and look at the axioms, this does not follow from the axioms, and I'll give an example on the next board of, I guess we already saw one, the partial order from before. It's not true that all elements are related, and I'll show that explicitly next. Okay, so given any y and x, we say that it covers some x, little x in x, if x is strictly less than y, and if there's any z in between x and y, then z must either be equal to x or equal to y. So there's nothing strictly between x and y. So when you have a poset, the Hasse diagram of the poset is a directed graph where the vertices are labeled by the elements of x, and the arrows exactly occur when for cover relations. So if y covers x, then there's an arrow. We draw an arrow from x to y. And we orient the Hasse diagram so that the smaller elements are below the larger elements, so it's kind of going upwards. Greater than or equal to is going up. And then finally, as I mentioned above, so less than or equal to is called a total order, or maybe sometimes a linear order, if for all x and y, either x is less than or equal to y or y is less than or equal to x. So this says that any two elements must be related to each other in the words of number 2. Okay, so next we're going to see an example of all of this, of all of these many, many definitions. Okay, so here's the example that illustrates all the definitions we had on the previous board. So again, it's the same example that we've been using. It's the first one that was the partial order. Maybe I should say this is a partial order. Remind us. Okay, so so first of all, we write 1 strictly less than 2 because 1 comma 2 is in R, so that means 1 is less than or equal to 2, right? This is the same thing as 1 is less than or equal to 2, but 1 is not equal to 2, and therefore 1 is strictly less than 2. Okay, number 2. 1 and 2 are related because 1 is less than or equal to 2, but 1 and 4 are not related. You'll see that if you look at this, look at the elements 1 comma 4, and neither 1 comma 4 nor 4 comma 1 is in R. maybe I should write that down too. So neither 1 comma 4 nor 4 comma 1 is in R. Oh, right. Great. So actually, notice that I've actually used two different notations here. I've used the notation R, and I've also used less than or equal to. So I guess I'm being a bit sloppy. So I should write this is the same as less than or equal to. Okay, so number 3, we have 1 is strictly less than 2, 2 is strictly less than 3, and 1 is strictly less than 3. Right, all of those are true. 1 comma 2, 1 comma 3, and 2 comma 3. Those are all in the relation. However, this one and this one are both covers, but this is not a cover because 2 is in between 1 and 3. But nothing is in between 1 and 2, and nothing is in between 2 and 3. And then the Hasa diagram is this diagram here. So maybe this is easier if I draw the one like that. And you can actually see, so all of these properties are really easy to read off from the Hasa diagram. So for example, 1 is strictly less than 2. They're not the same element, but 1 is less than 2. 1 and 2 are related. There's an arrow from 1 to 2, but 1 and 4 are not related because there's no arrow between 1 and 4, either in either direction, right? And we've labeled all the covers by arrows, which means that you can just read off the covers exactly. So whenever there's an arrow, there's a cover, and whenever there isn't an arrow, there's no cover, right? 1 is still less than 3 because it's sort of the conjunction of 2 covers, but there is no arrow from 1 to 3, so it's not a cover. Because, and in particular, 2 is in between 1 and 3. And this is not a total order because 1 is not related to 4. So right, 1 is not related to 4, so it can't be a total order. It's not true that any 2 elements are related to each other. My remark is that you have a total order if and only if the Hasa diagram is just a line. So again, this whether you have a total order or not is very easy to read off from the Hasa diagram. Great.